好。
Good afternoon. I'm the recorder today for problem number 9, circle of light. Okay, so first let's take a look at the problem statement. The problem statement tells us that when we aim a laser beam at the wire, we can observe a circle of light if we place a screen perpendicular to the wire. And the problem statement asks us to investigate this phenomenon and also investigate how the circle depends on the parameters of the experiment. And so in our report, we actually explain this phenomenon using our reflection and interference models, and also we try to investigate how this circle of light actually changes with these parameters in our experiment, such as the distance to the screen and also the radius of the wire, and so on. And so first, let's take a look at the phenomenon. Okay, so we can find that as we aim a laser beam at a wire from above, we can observe a circle of light. We can observe a circle of light, as we can see in this picture, in which the upper illuminance is larger than the lower illuminance. And also near the bright point at the bottom, we can actually observe bright and dark fringes here, which we actually hypothesize are interference patterns. And so for the outline of our report, we'll first have a theoretical approach with our geometrical optics and also our physical optics. Then next we will give a simulation made by VPython to verify our reflection model. And finally we will have experiments to verify both models and also investigate, as the problem statement asks, how the relevant parameters will actually influence the circle of light. And so for the phenomenon, we actually hypothesize that the shape of the circle is caused by reflection, while the bright and dark fringes that we observe are actually interference patterns. And so for our reflection model, we will first talk about the formation of the light cone. And so when the light beam hits the wire, we know that the x direction will not be influenced by the reflection. So now we can just look at the YZ profile of the wire, in which the incident angle theta and the angle between the reflected ray and the incident ray phi actually has a simple relationship, which is phi is equal to 2 theta. And so we know that in our experiments, theta actually ranges from -90 to 90 degrees. And so therefore we can conclude that phi actually ranges from 0 to 360 degrees, which means that the rays are actually reflected in all directions. And now from this picture, we can actually conclude two things. The first is that the illuminance of the upper circle will clearly be larger than that of the lower circle, since the energy distribution in the middle angles are actually much larger than those of the higher angles. And also, in order for a full circle to form, the radius of the laser beam actually has to be larger than the radius of the wire, as we can clearly observe. So if we combine the Vy and Vz vectors, again with the original Vx vector, we can find that the light cone actually forms after the laser beam hits the wire. And so we can conclude that if we place the screen perpendicular to the wire, then we can observe a circle of light on the screen. So we can conclude that the circular pattern of the light is actually caused by reflection, and that the light will scatter into a light cone after hitting the wire. And if we define the incident angle as theta, and the distance between the wire and the screen as L, and finally the radius of the circle as R, then we can find that these parameters actually have a simple relationship, which is R is equal to L cotangent theta.
升级一下，升级一下。喝水，喝水，喝水，喝5万块的升级一下。5万砸钱买电脑。在干嘛？在旁边队友。看，这样连队友。
因为它这档案很大嘛，这开这就会。
Okay, so actually we verify our reflection model by spreading powder onto our experiments. And actually we can find that the path of the light beam is actually a circular cone, just as we said in our theoretical model. And so next we generalize the situation into non-perpendicular streams, and unlike what the problem statement asked us, which is a perpendicular spheres that cut tangentially with the ellipse that its sphere focuses. And from the geometrical relationships, we can actually calculate the semi-major axis A and the semi-minor axis B of this ellipse. And so if we define the tilt angle of the screen as phi, then we actually, from geometrical relationships, we can find that A is equal to this equation. And from this circle that cuts tangentially with the focus of the ellipse and also with the side of this triangle, which is the side of the light cone, we can actually find that the semi-minor axis is equal to the equation at the bottom of the page. And so for our interference model, in our reflection model, you might have noticed that there should be a gap with the width of r in the middle of the bright point, which is shaded by the wire. But actually, we find that there is a certain luminance there, which means that it is not totally dark. So we can fully explain this using our interference model, and also we explain these bright and dark fringes that we can observe clearly on the sides are also caused by interference. And so if we look again at a Wisen profile of the wire, we can find that the 2 points in which the laser beam is not actually shaded by the wire are 2-point light sources which give off light waves that forms interference patterns on the right side. And so we know that this can actually be related to the common double slit interference experiment, in which we all know that the spacing of the fringes is actually delta, which is equal to lambda L divided by d. And so for our simulation, this is the code that we use in which we generate the laser beam as a circular panel of light points. And also for the reflection, we define it using vectors. Okay, and so here's a demonstration video of our simulation, which I actually don't have the video. And so we have a comparison of the circle from the simulation and the circle from the experiment. And we can find that actually they have a high similarity, which means that we have verified our reflection model with the Python simulation. And next we have a demonstration of the tilted screen, in which I also don't have the video. So again, we will compare the oval in our simulation to the circle of our experiments, and we can find that these two shapes also have a high similarity. And so for our experiments, this is the setup that we use in which we aim a laser beam at a certain angle at the wire that can be controlled. And actually we have a screen at the back of the wire in which we can adjust the tilt angle. And so for the parameters, we will have these parameters in our two models, in which we will investigate separately the radius of the circle of light and also the semi-major axis and the semi-minor axis of the ovals. And finally, we investigate the spacing of the fringes delta in the interference model. And so for our reflection model, the first parameter is the incident angle, in which we find as we increase cotangent theta, the radius of the circle actually increases proportionally to the value of cotangent theta, which matches our theoretical line. And also for the distance to the screen, as we increase the distance between the screen and the wire, we can find that the radius of the circle also increases proportionally with the distance, which also matches our theoretical explanation. And our third parameter will be the tilt angle of the screen, in which actually the shape changes as we increase the tilt angle from a circle to an ellipse. And so we actually compare the length of the semi-major axis A, and we can find that it is actually a hyperbolic-like line in which it actually matches our theory. And finally, for the wire parameter, we can find that even though we increase the radius of the wire, the radius of the circle actually does not change. And the only thing that changes is actually the thickness of the circle, which means that the wire we actually investigate a bigger circle also. And so for the wire diameter, we can see just as in our observations that the radius of the wire actually does not influence the radius of the circle itself. And so for the interference model, we actually measure the spacing of the fringes delta using Tracker, which is the analysis software in our experiments. And also, the first parameter is the distance to the screen, and we can find that as we increase the distance, the spacing of the fringes will also increase proportionally with the distance, which matches our theoretical calculations. And for the second parameter, which is the wire diameter, we find that as we increase the wire diameter, the relationship between d and the radius, the spacing of the fringes is actually an inversely proportional relationship, which also matches our theoretical line. And the final parameter is the wavelength know that the bright and dark fringes that we observe in the observation, and also the shade of the wire that actually should have a gap with the width of r in the middle of the bright point is also filled by interference. And so, as a conclusion, the simulation we made actually verified our reflection model, and by comparing the simulation to the experiment, and so we find that the similarity between these two circles that are actually quite common, we have verified the theory that we have derived. And so for the distance between for the reflection model, we find that r is equal to L cotangent theta, in which we verify in our experiments that r is proportional to both L and cotangent theta. And the right picture is the one in which we generalize the screen angle, which is phi. And so we also verify in our experiments that the change in the semi-major axis and the semi-minor axis in our experiments also match those of our calculations. And finally, for the interference model, we find that in our calculations, we assume that the interference patterns we observe in our experiments are actually caused by double slit interference, in which we all know that the calculation for the spacing of fringes is actually phi is equal to lambda, delta is equal to lambda L divided by d. And we also verify in our experiments that the spacing of the fringes delta is proportional to lambda and L, while it is inversely proportional to d. So that is all for our important things.
他讲英语比老外还快。用高铁哦。然后9时的时候你可以讲那种火箭好不好？刚好而已。我的2分之1说到我的具有伤害。
来，那个来源新闻那一组，赶快问一下有没有看有什么新闻发生？来，他最近哦，那个你看他们做了一个动画，那个其实很炫的，就是他都模拟一个光子，他就这样打到那个底丝，然后就打完之后散开，然后就全面转圈。啊，那个效果啊，他因为他在电脑都知道。还有有些，那有对，还有那个还有那个上课员啊，王一峰，你们可以跟他问好，但原则上不要用他的，你们自己要学着去把它呈现出来。不要因为你要真的做过才知道在干嘛。
翻译这个。作业很大哎。
来，看，现在看人太好了。
对啊。结婚一个，然后台湾的开玩笑。受完全受。Copyright。我没看你打我，我可能只能问他标题。你可以讲这些你说你在干嘛？没有，原来的只是思考的那一点。你们他是阿波的吗？他都有。以后啊，2场。哦，一样，都是同一集。还跟阿波比较强，然后就是以阿波本身的标准。我们要做哪一题啊？你直接用它的包，然后把它改成中式。用它的包，其他泡的，然后没有就把它的包学起来。全部学会了。
Okay, so I'm the problem number 6 magnifier. And so this is the problem statement. First of all, it teaches us how to create a glider, and then it tells us to find the power and just in the middle of the glider and then just release it. So the problem statement asks us to investigate the solution. So this is our observation video. As you can see, some sort of lift force causes the glider to go up and then it goes down. So we're going to investigate what caused the gliders to move up. will be smaller than the normal pressure. So obviously there will be a lift force. So first we're going to move on to our theoretical approach. This is our content. First of all, we're going to find the lift force, and then we're going to apply it to the glider. And then we're going to compare the lift force with the theoretical one. And then we're going to find an equation of motion, and as we'll see various trajectories. So to find the lift force, first of all, we consider it as a rotational incompressible flow. First of all, since it is the rotation of the flow of it equals to 0, and since it is incompressible, the divergence is equals to 0. And we combine these two equations, we can get that the Laplacian of it equals to 0. And since it is 0, so we can expand it by cylindrical coordinates, which is shown over here. And so it is solved by several variables with the boundary condition that is shown as this. And so after calculation, we can get the solution. And then, first of all, in our experimental model, the ball has a velocity, but in our theoretical, we'll assume that the ball has no velocity, but instead the airflow has a velocity. So, and then we're going to define circulation. We define it as the line flow of the fluid velocity around the flow's boundary, which in our case, the circulation equals to omega 2 pi r squared, which omega is the angular velocity of the glider. And so, after doing some calculation and substituting the velocity distribution inside our equation, we can get the pressure distribution of the glider. And then we let A, B, C to be 3 coefficients. And so we let the equation to be like this. So these are the calculations that we did. We just simply do integration to find the pressure distribution. And so we can find out the total force, the lift force that acts on unit length equals to negative rho v omega. And then so finally we find the velocity distribution and also the pressure distribution. Now we get the force that acts on unit length. So we're going to apply to the glider. So from our previous discussion, we found that the lift force that acts on unit length equals to negative rho v omega. And for our glider system, again the circulation is defined before, and it is shown as this omega 2 pi r squared. And so after we know the direction, we can know that the force acting on unit length equals to this. And so next we do integration to find out the total lift force around the glider, and it is shown as this. And so after doing calculation, the total lift force is shown as this. G multiply omega cross b, which G is the shear factor, which we've got different radius of the glider. And so for our through our previous calculation, we found out the theoretical lift force that acts on the glider. But now we're going to construct an experiment to find out the actual lift force that will cause on the glider. And this is our setup. First of all, this is a spinning motor, and a cylinder is shown as there, and a scale, a high-speed camera to track its angular velocity, and an anemometer to track the velocity of the airflow. And so this is our observation video. And we can observe that the scale, there will be a different value of the scale below here, and we can know that the force that actually acts on the glider. So there are two parameters that we change here in our experiment. First of all, we change different length of the glider and also the radius of the glider. And so first of all, this is the different length of the glider versus the lift force that acts on it, and the red one is the theoretical one, and the blue dots are the one that we actually construct in our experiment. The reason why it's always smaller than the theoretical one is because there will be a turbulent flow that comes behind the glider, and because we neglect this part during our calculations. And again, this is the different radius of the glider versus the lift force. found the equation of the height of the drag force by knowing its Reynolds number, and we know that it's proportional to the velocity. And G is the gravity acceleration. So the differential equation was solved by Mathematica. As you see, we input various, we input different parameters, and it is shown as this. And the equation was solved by Mathematica, which the equation of motion is shown as this. And so now we're going to see various trajectories. So we presume that to plot different trajectories under different initial conditions, and it is shown as this. For the left part, we change different launch angle while we fix all of the other parameters. And the equation of trajectory is shown as this. And as the right one, we change different angular velocity, but at the same time we fix all of the parameters. So after taking a close look, we can sort the trajectory into three kinds: type A with a loop, type B with singularity, and type C just a single motion that has nothing specific. And now we're going to move on to our experiment to test various trajectories. First of all, this is our setup with two high-speed camera. High-speed camera 1 is to track its initial velocity and initial angular velocity, and high-speed camera 2 is just to track its whole trajectories. And so this is our procedure, which is very easy. We just launch the glider by hand, and we use two high-speed cameras to catch different trajectories. And so we use tracker to track down the trajectory, which is shown as this. And as you can see, the trajectory is shown as this. So for our experiment results, again, we're going to find different types of trajectory. So this is type A. Because in this edition we forgot to input the video inside. This is a type A trajectory. And as you can see, it forms a loop here. I think that is caused by different initial launching angles. As you can see, the acceleration decreases more because of the initial angle here is much more bigger. And so, first of all, as you can see, the lift force which acts to the circle of the middle of the circle, and it is shown as this. And these are different parts of where the force interaction of the force and why it will form a loop. And for type B, this is the trajectory, just so it's a singularity. And so this is, we believe that when it's gone to the toughest part, as you can see, we believe that the lift force is not as big to create a loop, so there will be nothing, there will be a singularity. And for type C, this is the trajectory. And again, so for our conclusion is that we derive the lift force from Bernoulli's equation by calculating the pressure distribution, also the velocity distribution, and we combine these two distributions, we can get the total lift force that acts on the glider. And also we can compare the lift force from theoretical with the experimental result, which we find out that the experimental result is always smaller than the theoretical one. And then an equation of motion was found for the glider, which we showed over there by calculating by method. And also we find out different